high voltage direct current, HVDC, transmission systems have become critical infrastructure in modern power grids, enabling efficient long-distance power transmission and interconnection between asynchronous AC systems. Among the various HVDC technologies, Line-Commutated Converter, LCC, HVDC systems using thyristor valves remain widely deployed for bulk power transmission due to their efficiency and cost-effectiveness. However, LCC HVDC systems are susceptible to a specific operational challenge known as commutation failure, CF, which can significantly impact system reliability and stability. Commutation failure occurs when a thyristor valve that should turn off continues conducting because the current fails to transfer to the next valve in the firing sequence. This phenomenon is particularly critical for system operators working with HVDC interconnections, as it can lead to power transfer interruptions, equipment stress, and in severe cases, cascading failures. Understanding the fundamentals of commutation, the causes and impacts of CF, and implementing appropriate mitigation strategies is essential for ensuring reliable operation of HVDC facilities. Fundamentals and causes of commutation failure. In LCC HVDC systems, commutation refers to the process of current transfer from one valve to the next using the AC system voltage. This process, known as natural commutation, requires each valve to turn on at the commanded firing angle, alpha, and turn off naturally when the current transfers to the next valve during the overlap interval, mu. Successful commutation depends on three critical factors: sufficient AC voltage magnitude, correct phase relationship, and adequate extinction angle, gamma, margin. Commutation failure occurs when the extinction angle approaches zero, gamma zero, meaning the valve does not regain forward blocking capability. The primary cause of commutation failure is AC voltage disturbance, particularly at the inverter station. Common triggering events include single line-to-ground, SLG, faults, line-to-line, LL, faults, three-phase faults, severe voltage dips, or phase angle jumps. These disturbances reduce the commutating voltage, increase the overlap angle mu, and eliminate the extinction margin gamma. Secondary contributing factors that increase CF risk include weak AC systems with low short-circuit ratio, SCR, high DC current orders, inaccurate firing angle control, harmonic distortion, improper transformer tap settings, and multi-in-feed HVDC interactions, MIDC. System operators must be particularly vigilant when operating HVDC facilities in weak AC networks or in multi-in-feed configurations where multiple HVDC links terminate in the same region. Impacts and risks of commutation failure. The physical effects of commutation failure are significant and can be observed on both the DC and AC sides of the system. During CF, two valves in the same bridge arm conduct simultaneously, creating a short circuit on the AC side of the converter. This results in a sharp rise in DC current, often exceeding 2 to 3 per unit, collapse or reversal of DC voltage, and temporary interruption of power transfer. On the DC side, these effects cause stress on valves, smoothing reactors, and transformers, potentially leading to valve misfiring or thermal damage. On the AC side, CF results in loss of active power transfer, reactive power imbalance, and voltage instability. At the system level, repeated commutation failures pose serious risks including HVDC blocking, power oscillations, loss of synchronism between grid areas, and in severe cases, blackout scenarios in interconnected grids. The recovery time following a CF event can be significant, especially in weak grids or multi-in-feed configurations. For system operators, these impacts translate to operational challenges, increased maintenance requirements, and potential reliability concerns. Understanding these risks is crucial for developing appropriate operational procedures and mitigation strategies to minimize the likelihood and impact of CF events. Assessment methods and mitigation strategies. Assessing the risk of commutation failure in HVDC systems involves both simulation-based and analytical methods. Electromagnetic transient, EMT, Simulation with detailed thyristor level modeling provides highly accurate results but is computationally intensive and unsuitable for large-scale planning studies. Analytical methods using indicators such as maximum permissible AC voltage dip, extinction angle margin, and critical fault clearing time, CFCT, are more suitable for screening studies, sensitivity analysis, and planning of protection and controls. Mitigation of commutation failure typically involves a multi-layered approach encompassing 4 major categories: protection and control optimization, auxiliary equipment installation, DC power coordination, and converter structure modification. Key control measures include extinction angle control, EAC, gamma minimum control, current order reduction during faults, fast fault detection and recovery logic, and advanced firing angle during voltage dips. Advanced approaches such as adaptive control based on AC voltage phase, model predictive control, MPC, and AI-based CF prediction are emerging research areas. Auxiliary equipment such as static VAR compensators, SVCs, StatComs, synchronous condensers, and dynamic braking resistors can support AC voltage, improve SCR, and increase commutation margin. DC power coordination strategies include coordinated power reduction during AC faults, power runback schemes, multi-terminal and multi-in-feed coordination, and emergency power shedding strategies. Converter structure modifications may involve series-connected converters, improved transformer design, enhanced valve cooling and ratings, or transition to voltage source converter, VSC, HVDC where feasible. Notably, VSC HVDC does not experience commutation failure since it does not rely on AC voltage for commutation. Real-world examples and operator recommendations. Commutation failure events have been documented globally, particularly in regions with weak AC systems, high-power LCC HVDC links, and multi-in-feed environments. Well-documented CF events have occurred in India's multi-in-feed HVDC systems, China's UHVDC inverter stations, Nordic interconnections, and parts of Europe with weak receiving grids. These events have provided valuable lessons, highlighting that AC grid strength is the single most important factor in preventing CF. Dynamic reactive support is essential, multi-in-feed interaction must be studied carefully, and operator training and fast protection coordination matter significantly. For system operators working with HVDC facilities, several practical recommendations emerge from the technical understanding of commutation failure. First, continuous monitoring of extinction angle and AC voltage conditions at inverter stations is essential for early detection of potential CF conditions.